Welcome to Lab 5, Antenna Parameters and Dipole Antenna. Dipole antenna is a very basic antenna. It's an appropriate antenna to learn about different parameters and characteristics of any antenna. So that's why I've chosen the dipole antenna, and we will study on the parameters, characteristics of the dipole antenna. We'll talk about antenna array and also the performances of that array and the difference between the single element antenna and the array antenna. So software we'll be using is CST Micro Studio, and before we go into the tutorial part, let's have a look at different parameters and different basics of antenna. So antenna can be considered as a transducer, as a very important part of any RF system, and this is basically that part that converts the EM wave from the transmission line into the radio free space waves. So that means if there is no antenna in an RF system, there would not be any wireless communication. And we have discussed on transmission line. We know about the source and the load system. So antenna can be considered as a load, which has to be matched completely with 50 ohm characteristic impedance with transmission line and the source to maximize the power radiated to the free space waves. So this is how the EM wave propagation happens. I think this has been covered in a theoretical classes, which is just to refresh that, whenever there is electric wave or electric field, there should be magnetic field, and vice versa, based on the Faraday's laws and also the Ampere-Circuitous laws. And normally the antenna at the feeding point, we feed some current or electricity into the antenna, into the radiating element, and that creates a magnetic field. Eventually the EM wave radiated into the free space as and propagates to the receiver side. So these are different types of antennas, just basics. And as I said, the dipole looks like an OIR. There are horn antennas. This is a microstrip patch antenna. It's a planar antenna by type. There are some directive and omnidirectional antennas. This is a radar antenna. So there are different types of antennas based on the applications and requirements of the system, of the wireless system. And the one thing to know that as you change the shape, as you change the different size of the antennas, definitely the antenna parameters and the characteristic will be changed. So return loss, well, this is just another way to say the S11 parameter, or the reflection coefficient, which involves the incident power and the reflected power and measured in decibel level. This is the return loss, just the negative of this is the reflection coefficient, just the negative of return loss. However, we want this. We have talked about that reflection coefficient, so which is always negative, and return loss is always positive for a passive antenna. Remember. So and bandwidth. I think we have talked about that minus 10 decibel level. Where we're talking about the S parameter, S11 particularly, and that across that minus 10 decibel level, if you calculate the frequency and if you divide this frequency range by the resonant frequency is the operating frequency, you should be able to get that beam width in terms, or the minus 10 decibel impedance bandwidth. And also, minus 10 decibel impedance bandwidth is really important to know, because anything above the minus 10 decibel, well, we can say that the antenna is not performing well, because the impedance is not properly matched and the power is getting reflected. Most of the power is getting reflected. So that means the reflection coefficient, the plot, it has to go below minus 10 decibel, which is the acceptable value for an antenna in terms of the transmission. Efficiency, this is just the typical efficiency that involves the radiated power and the dissipated power. Most of the dissipated power of an antenna is called by the ohmic loss, and this is also a very important parameter. Then moving on, the gain and directivity. The directivity is the measurement of an antenna. That means how directed the beam can be to the desired direction. Okay. So we talked about that omnidirectional and directive antenna. So omnidirectional is just that antenna that actually radiates to the entire area, surrounding area of the antenna, or 360 degrees area. In contrast to that, directive antenna, they actually directs the beam toward the desired direction rather than radiating omnidirectionally. The gain is pretty much related to that, except that in directive the efficiency is not counted. However, gain involves that efficiency. This is also a very much important parameter. Okay, so let's move on. There are some regions of radiations when we're talking about the antenna. I'm not being too much detailed because we have to start the tutorial soon. However, it's good to know that there are three different fields of radiation. The first one is called non-radiating. It's pretty much adjacent to the antenna, and then we're having that radiating. We call the first one reactive. Then we call the second one, which is called radiating near field. This is here the reactive field does not exist. This is also called Fresnel region. But more importantly, the far field, which is called Fraunhofer region, and that is something that we have to know, because this is where the antenna, the power is to be considered that it does not diminish with the distance from the antenna. And this is the region where actually measure the you see the radiation pattern, and we measure the radiation pattern. And as you can see from this expression that this is highly relevant, highly dependent with the parameter called D, which is the parameter highest dimension of the antenna, and lambda, the operating frequency. So in this region, the fields are proportional to 1 over R, in contrast to that 1 over R square in the radiated near field, and 1 over R cube, which means the power vanishes quickly here. So actually we cannot measure practically anything in this region. So this is the most appropriate region of antenna measurement. And let's move on. So yes, now we are going to talk about the dipole antenna. We call this half-wave dipole antenna. This is just an wire, as I mentioned before, and 2 wire segments having a total length equal to half the wavelength of the operating frequency. And the antenna is having this impedance, which is 73.2 plus J425, 42.5. However, we are ignoring the reactive or the imaginary part here. That means the to be able to match the antenna to a transmission line, it is much easier if the antenna's length is slightly shorter than lambda over 2. As we mentioned that this is a half wavelength. However, we are in this case actually the length is little shorter than half lambda over 2. This is because we have ignored this imaginary part that decreases the length a little shorter, equivalent length a little shorter. So basically, instead of being 0.5 lambda, we will be considering this length is 0.47 lambda. And then the array, well, this is just the combination of different antennas, different elements. We can call those antennas element. So in this case, multiple antennas will be acting, and they will have impact on the directivity, gain, and other radiation pattern. So basically, it can have multiple feeds, or it can have single feed. Let's say we're having like 4 or 5 or 6 elements together, and you are feeding them together, and they will create some resultant radiation patterns as per the requirement. We'll get to know how they are changing from what that was the case of a single element antenna. So, for example, if a single element dipole antenna gives you the omnidirectional pattern, and if you create some arrays with the same antenna, there could be more directive patterns instead of being the omnidirectional patterns. So, as we done with some theoretical parts, if you are having some questions, just feel free to ask. Maybe I can provide you some appropriate sources so that you can learn more about the antennas. So now let's move on to the laboratory procedure. So, as we mentioned before, that dipole is a wire type of antenna, so you have to choose from the template antenna wire, and we have to change the recommended solver by the CS from integral equation to the time domain. However, we really don't have to worry about that because typically we use the time domain solver. These are some free setups, units. We have done that before. We have been always using the millimeter and gigahertz, background things, boundaries things. So in this section, you are supposed to design a dipole antenna. A very useful method when designing an antenna in CST microwave is to parameterize your design variables. What is it? What is this? Okay, so parameterize means that let's zoom that in a bit. So whenever we just click on some model things, if you remember from the CST, and you always put a value here, the break. Let me show that in the CST. So let's open up a new file, template. It's going to be microwave wire antennas. Normally it's going to be wire, as I mentioned before, and this is time domain. So this is the typical setup. Don't change anything here. We are not done. We haven't seen that yet, so we can do that later. The frequency setup things. Done. So, which I was talking about, if you go to modeling, click on any object, and if you just click on here, So you see, in this box, you see some values here. So there's another way, smart way, called parameterize. That means you just define some variables. For example, you wanna, let's say, x max, which is width, and this is width. So if you just parameterize, that means you are having an option to put any value here rather than just changing the whole thing again and again. Or you can just click on that thing. Let's say, put the value, let's say, which is 2, and there you go. So we just parameterize as values. That means whenever you click, rather than just clicking on that thing, if you want to change that dimension, if you just put it here, double click, you see the parameter list here. Just double click on that thing, put any value you like. Let's say I'm going to put 5. This is asking to press F7 or parametric update. You have to do that, otherwise this is not going to be effective. And there you go. So every time you don't have to go there. If you just parameterize the brick, let's say you want to parameterize the another one, which is across the Y. Let's say this is length of the brick, L for length, or you can write the whole thing. This is a parameter, this is a variable, and so this is another new variable, length. In the previous time it was W, this is length. That means this will be looking for a value now. Let's say this is 6. There we go. So we are done. So next time you don't have to go there again and again. Rather, you can just put the value here. Let's say you want to make it more longer, 10. Press enter, F7, and the parametric update. You can find this here. Sometimes we are just getting confused. We don't find that parametric update. You can press F7, which doesn't work in my computer's case. So normally I have to go back to the home button, and I will be looking for this, and that's it. It's a very handy option rather than going to this tree every time, double clicking on thing and changing. It's very smarter way to define some parameters or variables for length, width, height, and you can just put whatever the value will be required at any point of your design or any point of your simulation. Okay, so this is what is explained here, which I have mentioned already. Maybe we will be using some of it in our today's design. So let's have a look at the question that you have to answer, the part of the report, which is to calculate the required dimension of the antenna so that it has a resonant frequency of 1 gigahertz. You know the formula, which is 0.47 lambda here. So that's pretty easy to determine lambda. If you know the lambda, if you know the frequency, which is 1 gigahertz, it's pretty much. You can get that lambda as well. C is equals f lambda. So you can get the value and you can get the length. One kind of cable is suitable for fitting the dipole antenna in terms of characteristic impedance. Well, this is something that you might want to research a little bit. Just answer whatever you can. I have the answer, but it's up to you. It's your assignment. But if you're stuck, just let me know. Maybe I can help you answering that question. Okay, so again, one of the most important field monitors which always used in the designing antenna is called far field or RCS monitor. So you have to do that from your CST to have a look into the far field monitor. So if you go there, just So if you go there, you see that field monitor somewhere. Let's say post processing or okay, there you go. You can get that from simulation. If you go to field monitor here, there are different field monitors. If we talked about the radiation pattern, so these things are really important um, to know the radiation pattern of that particular of a particular antenna. So this is a field. We haven't set up this frequency yet. We'll do that in a moment. So so we are about to create a dipole antenna. Remember the size of the dipole antenna? Let me show you the design first. Okay. You see, there are two different wires, which is here. This is the feed point, and the wires are having total length of 0.47 lambda. Again, it's up to you to calculate the lambda and times 0.47. However, you see there is a gap here. This gap is of 2 millimeter. You see that, and small distance of approximately 2 millimeter. Right into that gap, you are putting that discrete port as your waveguide port, as the exciting port of the antenna. So again, I think you are familiar to build a cylinder. The cylinder is having a radius of 1 millimeter, and you have to put two cylinders, and right in the middle you have to put the discrete port. Okay, so this was already covered in the tutorial, so that's why I'm just trying to show you how it will look like after you have designed the dipole antenna. So again, when we go back to the modeling, and you see that cylinder, you have to create two cylinders, okay, like this, with a gap of 2 millimeter, and the cylinder both and the entire length of the cylinder, which is 0.47 lambda. However, you have to consider this 2 millimeter as well. Okay, so you can see from the parameter list, you just click on that components just to double check. Remember I mentioned the length of the dipole antenna is 0.47 lambda, which is a half-wave dipole. So here, this is the way you see the radius of that cylinder, which is 0.5. That means 1 millimeter diameter. This is how we have defined the x minimum and x max, which is the length. Remember, this is the gap here, so which is 2 millimeter, and length is 141 millimeters. This is the entire length of this particular whole antenna. Okay, so this one has to be like minus L/2. So this is how we have defined. Remember, our target is to make this dipole antenna. Let's calculate how to calculate this particular. Let's pick a point here. pick face center. So done. A good way to measure any length in CST. You see 69.5 millimeter of this half of the entire structure. So 69.5 times 2 of this one as well, so it's going to be making up 141 altogether. Okay. I hope you can do it by yourself. Just remember to pick cylinder, and you have to make that length somehow 141 millimeters with a gap here. This gap has to be like 2 millimeter, and the radius of the cylinder got to be 1 millimeter. And then you have to put this port here. This is going to be a discrete port. Then you have to choose the point here, pick this face, pick face center, and you have to pick this one as well, pick face center. Not going to do it now because this is already done. Then you go to the simulation and discrete port. If you click on discrete port, this will be like this. Okay. So this is about the single dipole antenna. Let's see what you have to do. To provide a plot of S1. Oh, okay. Before that, you have to set that things up. I hope this has already been set up. You don't have to do that pretty much really. Just go make sure one thing, that field monitor. Go to field monitor. And before that, let's define the frequency first. So it's already been defined, which is 0.5 here and 1.5 here. And then go to the field monitor here. You see that radio buttons, sorry, and this E field here, and our observation frequency is going to be 1 gigahertz, which is written there. And then press apply. If you want to click on that thing, press apply. If you click on that thing far field, press apply. Okay, so this is how you'll be setting up that field monitor so that you can watch the radiation pattern completely, E field and H field and others. Okay, and then you run the simulation, and you'll be watching first. Probably you have to answer this question first, then provide a plot of S11 versus frequency for the dipole antenna, and clearly show the antenna resonant frequency. So is the resonant frequency calculated by CST consistent with your design requirement? Okay. To have a look into that, again, this simulation is already been done. So let's click on that result. Click on one result. Click on S parameters, class field, and S11. So, well, it's not pretty much the thing that we have been looking for, which is 1 gigahertz, but that should be fine. It's 0.99. Okay, and so this is our S11 S11 plot. The other name is reflection coefficient. We talked about that minus 10 decibel level. This is way below. The minus 10 decibel is almost as minus 30, and which is pretty much acceptable. The frequency is 0.99. Okay. To have a look into that, you'll see that to put the marker, I'm not sure whether you have seen that in the tutorial of CST, but let me show that. There you go. Okay. So I'm gonna be, let's delete that. Okay, so you wanna put a marker here. Just put a curve marker, curve marker here. There we go. Okay, so what else we have to do? Is the resonant frequency calculated by CST consistent with your design requirement? Well, have some comment. This is not pretty much consistent, but it's okay. And so you can have some comments on that. Maybe you can explain some reasons on that. What could be the reason? Then what is the minus 10 decibel bandwidth of the antenna? Okay. So you see the minus 10 decibel, we mentioned that this is a bandwidth. So that means you have to find this frequency here. You have to find that frequency here. And just the range over the resonant frequency. That is how you have to calculate. It's already explained in the, if you go back, there we go. So if you just have a look here, you should be able to calculate that. Then, well, something you can look into is that go to post-processing. If you want to look at the impedance impedance plot, imaginary person, real and imaginary parts of impedance, you know already from your which is 73.2. Remember, for the dipole is not the 70, it's 50 ohms. This is 73.2 or 73 above 73.2 impedance. It's a little bit different from what we know, which is the 50 ohm characteristic impedance. So go to post-processing, then go to impedance matrix here. There we go. So what is it here is, well, there is no marker here, so we have to find the lowest value, which is here. Let's put a marker here. Frequency was right there. Put a 0.97 or 0.98 or 0.99, whatever it is, which is 68. Well, again, this is a little off from what we were looking for, which is 73. But again, it could be due to the lot of reasons. So for now, we can just ignore. Maybe we can make it better. But that is more important, that you know how to do these things and what is it, what are the things. So this is the impedance of dipole. For other antennas, most antennas, this is 50, but this is 73.2 for the dipole. It's an exceptional case. Okay. Right, so now let's have a look into the far field things. This is a very cool feature, and some three-dimensional, very nice to look pictures. Let's have a look into those. So show the 3D far field in your logbook. From the 3D far field pattern, and provide with the directivity, radiation efficiency, and total efficiency of the antenna. And provide a polar plot of the plane and H plane of antenna. Okay, that is why we have done that far field monitor setup. Remember? So go to, if you do that, you want to do that. Then let's go here and then. This is a polar plot. This is a frequency 0.99 gigahertz. You can see that main lobe magnitude, and if you wanna change that thing to theta, that's the omnidirectional thing. This is you can call when you set theta as constant, or horizontal things, horizontally how the antenna will, if you hold the antenna like this, that's you wanna look into the far field plot, go to the 3D pattern. There you go. There should be an option if you want to see the structure. That's very nice thing, and make it a little bit transparent. See that. Yeah, see that structure here. So this is how the antenna will actually radiate. This is a two-dimensional things, and if you want to look into the three-dimensional pattern, there we go. Okay. So yeah, if you have a look into this way, and if you have a look into this way, pretty much similar. However, so that means the structure is like this, just lying this way. And if you want to rotate the thing this way, this is another way. So what are, okay, there are a lot more things that you can get from here. Let's say directivity. There's the directivity, which is 2.223 dBi. You can have a look into the gain, which is 2.193 dBi. And what more, also provide a polar plot of the E plane and H plane. There should be radiation efficiency as well, which is here, the total efficiency. And you can see the realized gain, the E field and H field. Let's go to the polar plot. That's the E field and that's the H field. Okay, so you can have some comments here. So this is something that normally we do whenever we're looking into the three-dimensional pattern here. But remember, you have to set that up before you run the simulation, otherwise it will not come up automatically. Okay. Just one thing to that you see, if you see that scale, you see the red thing is more stronger and the blue thing is the less stronger. So whatever the things as you go along the axis to the up, that means, and if you just try to correlate this diagrams with this scale, that means we are having this area the maximum radiation, or maximum H field. How about the E field? It's the same thing. If you want to have a look at the gain, we are having the maximum gain. That means red means here, okay, and the minimum is here at the points. If you look at that, okay. All right, so this is how you have to interpret the radiation pattern things. So what next is so regarding the lab question 7, I think we have answered most of it except the main lobe and angular width of the antenna, which you can find from here. Go to main lobe. Sorry, let me just go there. Yeah, you see the direction here. Main lobe direction, angular width, all you can find here. Just select the directivity. Normally, you know, directivity is a measure of angle. So you see the main lobe direction is 0.0 degree and angular width is 8.3 degree. And main lobe magnitude is 2.2. So anything you like, you can just have a look here. Remember, the dipole antenna is not a radioactive antenna, sorry, directive antenna. So we are having, if you just click on that thing, you see there is no particular directivity here. This along here. When I set the theta constant, that means this antenna actually is radiating all the way, everywhere. Okay. So now, for the next part, we will have a look at the array, how to create some arrays, and we'll have a look at the different format, different orientation of that array and how the performance will be changed accordingly. So to create some arrays, you just have to copy the whole or entire single element of dipole antenna which already have designed with CST, and you have to keep that. You have to just copy the whole element and keep them side by side. Now the question is, at what distance? Okay, the appropriate distance between the elements within an array roughly has to be lambda over 2. So you know that lambda already, and you can calculate the distance in that case. So let me have a look once you are done with the copy and how the whole thing will look like. There we go. So to make it better to look at, so here, and you see the distance between these two elements is pretty important. Remember, it has to be lambda over 2. So you can calculate the lambda from 1 gigahertz frequency. You know the light velocity, and you can easily calculate the lambda. So distance between these two elements has to be lambda over 2, and and you know how to copy these things from this. Let me show you that. For example, this is your pole 1, and if you go to modeling, transfer, if you click on the translate thing, definitely you have to copy. Check on that copy, otherwise you will just shifting the element without having the first copy here. And then, well, if you just copy one time, or I know, I'm assuming that you know that already from the CST tutorial already. Just to recall, refresh. So we are just repeating for once, and remember, if you are moving along the y-axis, so put some value here, which is lambda over 2, the calculated value. All right. Then we will be done. So I'm just cancelling since I'm done already. So remember, use the translate function here, and there we go. One thing I forgot to mention before, when we were designing the first element, your material would be copper. Okay, copper annealed. You know how to set up the material for your design. Okay, so now let's go and check the other questions. Oh, we have to change a little bit because this is no more a single element. So once you are done, copy it. The whole entire thing. Entire thing means, for example, you have to copy the port as well. So go to the port. You see the port, and then transform the whole thing. So remember, I should have mentioned that before. When you copy the things or copy the previously designed single element antenna, don't forget to copy the port. Otherwise, you have to define the port again, and that could be a wrong thing. So don't forget to copy the port as well. Okay, so now that you are just having exact copy along with the ports, you have to tweak a little bit into the simulation setup. Let's have a look into that. Go to the time domain solver, go to simulation, solver setup, and then go to selection, and you have to select all port here. Okay. So an active simultaneous excitation, and solve the simulation again. So simultaneous excitation, excitation list, so then excitation all, and simultaneous. Sequential is normally used for just single element, and for the array normally you use the simultaneous. So don't forget and don't check on all of the ports here. It will look like this, and once you are done, press OK. Okay, since I'm done, I need to show you the results, so I'm not going to mess it up with my design. So I'm just coming back to previous command. So in this case, as we are done with the time domain solver setup, you can see the result now. To look at the result, this time you are not interested in the S parameter, rather you are interested in F parameter. Okay, and there we go. So this is your array response of equivalent to that S parameter. Okay, if you click on that S parameter things, it's going to be the same all the way, but however, click on that F parameter, that's the result. So provide the 3D and polar radiation pattern. However, we are more interested in the 3D radiation pattern. Let's have a look into those things. There we go. You see two antenna here, a little change. You see the gain is pretty much double that we had in our previous case. Let's have a look. Go back into the previous things. 2.2, okay, the gain 2.19. How about this time? 5.86. And you see the response of directivity is going to be changed as well. 6, whereas for the single element is 2.23. So it's going to be changed a lot. And let's have a look at the polar plot here. Okay, little change here. Little change. See the angular things here? It's going to be changing a little bit. Okay. So you need to save these pictures. You can have some comments if you like, how they are changing with plan and H plane along the E field and H field. These things. Now we want to copy more. We want to make increase the number of elements. So in that case, for this case, we are having that we are having just 2 elements here side by side. Okay. Okay. So we are having two elements. So let's copy more. I mean, let's copy the whole two things and translate using the translating function here. Remember, don't forget to copy the code. So there will be two more elements in a linear pattern, which is like this. And remember, the distance between all the elements is lambda over 2. Now, let's have a look into the far field pattern. You see, this is highly directive, and you see the directivity. Okay, if you want to see the gain, pretty much high, and I'm sure this is almost a directive antenna. That means the nature of dipole antenna is being omnidirectional. However, just making a linear 4-element array antenna, the whole resultant radiation pattern is utterly changed. And let's have a look how that has been changed here. You see that it's hard to tell from here, but look at this parameter here. This is pretty much changed. And also, if you go to click on that H field, hard to tell from here, but you see that angle. But this is amazing. I mean, if you go back to the single element and click on that field, this is pretty much omnidirectional. However, from here with 4 elements, this is how it will look. And you can change further if you just increase the elements, or you can change the alignment or the orientations, or if you go click on that thing, you can put some here, you can put some here, you can put more. Okay, this is a linear things. Let's try something else. Let's put in a square pattern, okay, which is here. So this is kind of like a little bit of three-dimensional things. You are having previous two things here. Now, instead of moving them side by side, you're just pulling them up or down. You can do that, okay? Just again, rather than translating them across the y-axis, maybe you can just translate them across the z-axis, okay? Now, let's have a look into the pattern. Yeah. The polar plot is pretty much changed. The angular width and other things have changed. Let's have a look at the three-dimensional things. So, the same antenna, if nothing is changed, the antenna parameters are all the same. You are just increasing the numbers. You are just setting up or tweaking up the solver, time domain solver, which we have done here. Remember, don't miss that step, that you have to change this, go to excitation list and changing this simultaneous and exciting all the ports together, 4 ports. Only then you'll be able to see how the array would be responding. So the main point, the whole point is that any array of any antenna, response of a single element antenna, and array of the same antenna could change a lot in terms of the radiation pattern, reactivity, gain. Even sometimes this is really required, that we want to make a very directive or very a radiation pattern with high gain. So particularly an array can improve the directivity and gain of any antenna system pretty much. And in most of the advanced RF system are using these days the array or multiple antenna systems for better result, for high directivity, for high gain, and for definitely for a higher bit rate. So we're pretty much done with today's sessions, and I hope it was quite useful for you and understandable the difference between the response of single element and the multiple element array antenna of the dipole antenna. And if you are just stuck at any point in the design procedure using the CST, just let me know, and we'll try to solve the problems and try to help you. So again, thank you very much. I hope you enjoyed today's lab session, and we will be using the array pattern more, and we'll be designing different antenna instead of the dipole, which is called CST microstrip patch antenna. And also we'll play with the array your design project of the whole course. So today's lab is going to be really advantageous and beneficial for you for your design project. So that's it. That's all for today. Thank you very much. I hope to see you in the next